Thanks. I will begin. Heavenly Father, we thank you for this day. Thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right, so I will start by saying a few things about the rational canonical form, just to try to explain more what it is, all right, and its existence. And so we're focused on a linear transformation from a finite dimensional vector space to a finite dimensional vector space over some field F. And basically the theorem is there exists a basis, beta, such that the matrix of T with respect to this basis is equal to block diagonal. So if I recall correctly, the companion matrix of A1 of X, the companion matrix of A2 of X, the companion matrix of A, let's say AM of X, where A1 of X, A2 of X, AM of X are the invariant factors for the fx module induced by T. So just to try to explain further, remember we have the divisibility conditions. A1 of X divides A2 of X, divides AM of X. And a little bit more theory for you here, where AM of X will be equal to the minimal polynomial for T. All right. So it's a monic polynomial of least degree, that when you plug the linear transformation in, you get the zero transformation. And another bit of the theory here is that the characteristic polynomial T of X, which is by the definition the determinant of X minus T, all right, where that X is understood to be X times the identity operator, then this characteristic polynomial is actually equal to the product of the invariant factors. The theorem is, one of the theorems we have is that the minimal polynomial divides the characteristic polynomial. All right. That's not especially surprising if you know this formula, right? I mean, it's like, oh, look, the minimal polynomial. So the minimal polynomial divides the characteristic polynomial, right? If you know this formula, then it's obviously true. But what's also true is that the characteristic polynomial divides a power of the minimal polynomial, right? And the way I tend to remember that is that the characteristic and minimal polynomial, they share the same factors, all right? So that's very limiting. If you give me a minimal polynomial and you give me something that's potentially a characteristic polynomial, I could strike it down as being impossible for any variety of reasons, if it didn't share the same factors and so forth. Okay, now the question is, how do you this basis, beta for V, how is it constructed, all right? So the way the basis, and what are these C's that I'm talking about? What are the C's? So here, the basis that I'm talking about in this theorem, beta, is constructed from the union of T-cyclic subbases. And what I mean by that is there exists a set of sort of like fundamental vectors, all right? There exists F1, F2, Fm, such that if we look at the, let's say beta 1 equal to F1, and then T of F1, and then T of F2, T squared on F1, all right? This is what's called a T-cyclic basis. A T-cyclic basis is generated from like one vector and then powers of T acting on the vector, right? Now this can't go on forever. Eventually there has to be some sort of linear dependence, all right? And so whatever the degree is of A1, let's say that the degree of A1 equals to R1, all right? If the degree A of 1 of x is equal to R1, then that means that how can I say this? Oh, I've lost count of my count. I think we go all the way to T R1 minus 1, that power of that acting on F. So that would be the first part of the basis. We have this fundamental vector F, and then we power to get the rest of it. And then this continues. Like there's a beta 2 that's similarly constructed. F2, TF2, TR2 minus 1, F2, all right? So the number of vectors in beta 1 is R1. The number of vectors in beta 2 is R2. Yes, Liam?
Okay, can you remind me what the minimal polynomial is?
We'll get back to it. But it's the polynomial of least degree, which when you plug in the linear transformation, you get 0.
Okay, gotcha. So that's specifically when you, okay, because I was wondering how it's possible that A1 of x divides, when all of those divide AM, if AM is the minimal polynomial.
Well, I wouldn't say that these, well, oh yes, they do. Never mind. I'm an idiot. Beta M, the last one, we of Fm, then T of Fm, TRM minus 1, Fm. All right, the number of things in this is Rm. All right, so I'm using R1, R2, Rm as the degrees of the invariant factors in like polynomial degrees, right? So if you take beta by the ordered union, like beta 1 union beta 2, maintaining the order, right? Then this basis, so constructed, will have a matrix for the linear transformation, which is in the so-called rational canonical form. Rational canonical form means it's a block diagonal with companion matrices down the block diagonal. I've not defined a companion matrix yet, but I will. I'm getting there. Sorry, this is one of those cart before the horse sort of lectures. But anyway, does this at least make sense? The counting here, I've got R1 things in here, R2 things in here. So like the number of things in beta is equal to R1 plus R2 plus plus Rm. that should be equal to the what? That should be equal to the dimension of V, right, if it's going to be a basis for V. But guess what the dimension of V is also equal to? It's also equal to the degree of the characteristic polynomial, right? You know this from your previous experience with eigenvectors and such. The degree of the characteristic polynomial is the dimension of the space you're working on, right? So I think at least things add up here. We've got enough. If you can actually find these vectors f1 through fm, right, such that these lists f1, t of f1, t squared of f1, and so forth and so on are linearly independent, and if you can do that and join these together, then you have a basis. All right? Thumb-and-foot actually explains explicitly how to calculate these f1 through fm's. He puts them in a matrix he calls p prime. And he describes how to construct this matrix from a systematic algorithm based on calculating the Smith normal form for the given matrix. If you pick a basis, right? Pick a basis, any basis, it gives you, the original matrix for T being A. You look at the Smith normal, look at xi minus A. You do the find the Smith normal form of it. Once you do that, the Smith normal form, and we'll talk more about this explicitly in detail as we go on this lecture, don't worry, I'm getting back to it. But the Smith normal form will actually explicitly tell you what the A1, A2, AM is. And also, if you track through the steps you did to get to the Smith normal form and follow the algorithm that's laid out in Thumb-and-foot, you can explicitly calculate the F1 through FM using the algorithm. That's not something I expect you to be able to do on the test in here because it involves a lot of bookkeeping, and it's just really inappropriate for an hour test, especially in an undergraduate course. But I would like you to know about it. That's why I'm telling you about it. All right. And I think there is one homework problem that probably kind of. See, I'm not sure. You could. Here's the thing. Yes, you could follow Thumb-and-foot's algorithm to find the F's, right? Or you could just kind of attack it directly because you know what you're looking for after you see what's going on in here. So it's probably easier for a small system to just attack it directly as a problem of matrix algebra, as we did in linear algebra. We find eigenvectors. We found the characteristic polynomial, right? Do you remember the Smith normal form from Math 321? You shouldn't. I didn't cover it. Okay? And if Dr. Scambortis covered it in 321, it'd be hilarious. But I don't think he did it. Wonder how much I'd have to bribe him to get him to do it. I don't know. I don't think I got enough money. Okay, so the companion matrix, just to give you a specific rundown there. If we have a of x equal to x to the power k plus bk minus 1, x to the power k minus 1 plus plus b1x plus b0, all right? Then the companion matrix CA of x has the following form. So it's got ones on the subdiagonal. All right. So, I mean, this is basically just this observation, right, guys? That T of, I mean, here's why we're interested in this. T of Fj is equal to F, j plus 1 for j equals to, well, 1, 2, all the way out until we get to k minus 1. I'm sorry, I'm digressing from my definition momentarily, just to try to connect with the basis. If you look at the basis, right, think about calculating the matrix with respect to such a basis. See how that works? To see what happens to F1, we look at T of F1. T of F1 is equal to the second thing in the basis. That's why we would have 0, 1, 0, 0, 0 for the first column. It has to do with that. If we look at the second thing in the basis and we take T of that, we get the third thing in the basis. That's why we want a companion matrix that has this 0, 0, 1 in the second. Yep.
So are you saying, so it's not like F2 from beta 1 or F1 from beta 1 and F2 from beta 2? The Fj and Fj plus 1 are talking about things in the same basis?
Oh, yeah, I'm sorry. Vj plus 1, where I'm thinking of V1 like F, and V2 like T of F, and V3 like T of F. Let me strip off the, I want to talk about a generic one of these. Thank you. That's helpful. But the thing is, this stops, all right, because eventually you get to the kth one, all right, and there, so eventually the one reaches the bottom, right? All right? All right. And then the last column, you end up with minus b k minus 1 minus b0 minus b1 minus b2 and so forth. So minus the coefficients of the matrix you're finding the companion matrix of. Let me make this less esoteric. For example, C of x squared plus 3x minus 2 is a 3 by 3 matrix. 3 by 3? Hey, let me make this cubic. It's more exciting. 3x squared minus 2x plus 1. There we go. So 3 by 3 matrix, 0, 1, 0, 0, 0, 1. Those are easy. And so here I do minus the constant term up here, and then I put a 2, and then a minus 3. So you wonder about the last column, right? Like what's happening with that last column? So T of Vk minus 1, right? Say this. Let me not. I don't have it. It's not it. My mind's not working. There is a simple reason for why this last column is that. It's just looking at the basis appropriately. Yeah.
Based on what we said, should it not be 2 minus 3 minus 1? You worked from... And actually, shouldn't it start with another one? Like, because it works its way up from the end, which is just a scalar. And then you go back to B1. So I feel like in this case it'd be minus 1, positive 2, minus 3. That is what you wrote. Okay. Never mind.
Oh, okay.
Sorry about that. Oh, shoot.
So in this, all right, very good. On
I
page,
understand this now.
on page 474, he gives a meaning to x bar k plus b k minus 1, x bar k minus 1 plus da 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 plus b b1 x bar plus b0 equal to there's a discussion leading up to this, what this X bar is. It's motivating the definition of the companion matrix, and it goes into proving what I've claimed today. But basically that, so this it shows you that this should be minus all those, and so this essentially is that last column in some sense, which is why you get the minuses. That's not a very compelling argument. I'm sorry. I'm going to stop talking about that because I actually have other things I can tell you, I think, more convincingly today, so I'm going to go on. Yeah.
Does it have to be, like the coefficient of the first thing, does it have to be 1?
Yes. So we do this for monic polynomials. Now there's a beautiful theorem. The determinant of x times the identity matrix of the appropriate size minus the companion matrix of A of x is equal to, here assuming that this is monic, it's just equal to A of x again. So the characteristic polynomial of a companion matrix is the polynomial for which it's the companion of. All right. So I can actually get to the point here. So here's the big picture. One, pick a basis and look at the matrix of T with respect to that basis, call it A, all right? And calculate xi minus A. And you can do row and column operations, and you get to what's called Smith normal form. We look at the Smith normal form, we can read off the invariant factors from that, and from each one of those invariant factors there will exist a T-cyclic subbasis. You string these together, it puts the matrix of the transformation into rational canonical form, where rational canonical form means it's a block diagonal like that. Now the beautiful thing about this is two matrices which are similar, all right, will have the same rational canonical form. All right. So you can test similarity of two matrices. You can test when two linear transformations are really the same transformation with respect to a different choice of coordinates, right? Because if they are, then there's a similarity transformation to go from one to the other. I mean, there's a whole host of things you can do with this rational canonical form. Let me actually show you. Well, this is the great debate for me. Should I show you the Smith normal? If you guys can wait to see the Smith normal form calculations at the end of class, it's more safe for me to do the not calculation at this point. All right, let's just hope technology works. I'm living dangerously because I want to put this away after I show you these things. But will I be able to? I don't know. So what I was trying to get at, guys, is there is the rational canonical form for a linear transformation is essentially unique. It's like the skeletal structure in some sense of a linear transformation. Theorem 14 tells you the rational canonical form of a linear transformation is unique. And Theorem 15 says S and T are similar linear transformations. The fx modules obtained from S and T are isomorphic. S and T have the same rational canonical form. These are equivalent statements, all right? So it's really nice. And then all of these things, of course, have equally useful applications to, oh, be quiet. Paul. No. Paul sent me some sort of media text. I hate that. So, I'll try not to belabor these too much, but this yes, yeah. Okay, so here's a matrix. Let's find the Smith normal form of it. Okay, what that amounts to. And by the way, Thumb has a proof that that does in fact calculate the invariant factors, right? That's not, I don't think that's immediately obvious, right? That is developed over a series of exercises in like section 12.1. And, you know, you're not responsible for connecting those two ideas. You can just use the Smith normal form as I'm saying. So we are taking a somewhat black box approach to module theory. I mean, we're using certain theorems without understanding, admit it. My apologies for that, but you guys said you want to study Galois theory, so I'm not going to spend another month on this, which is what it would take to prove these things, at least a month. Okay, so xi minus a is this, and then how did I get from here to here? What did I do? Right, I switched rows 1 and 3. That's a kind of a low-tech step. This one, what I did was, I did row 1 plus 2 row 2, and this is interesting. Check this out. Row 3 minus x minus 2 row 1. So these calculations are happening in the fx module. We're allowed to multiply by, well, anyway, so this is an allowed calculation anyway in the fx module context here, and that gets us to this. And then the game is every time, so you look at, I mean, this is kind of complicated, but the way these calculations work is you look at it and you look for the greatest common divisor of all the things in play. What's the greatest common divisor of all these? Well, fun fact, if you have polynomials with different roots, they're linearly independent. I mean, they're relatively prime. It's like x minus a and x minus b, if a and b are not equal. These have a greatest common divisor of 1 in fx. So that means that the GCD of the original matrix is 1, which means I'm trying to put a 1 up here and then clear out below and to the side using row and column operations. So to get rid of this and this, I subtracted column 1 from column 2, and I subtracted x minus 5 times column 1 from column 3, which is hard to see because that's the thing, is once you have zeros here, there's no even thinking involved, right? It doesn't even mess with these two, but it clears this out. Yep.
Did you say you're trying to get a 1 in the top left corner?
Yes. Or more generally, the GCD of what's involved. And then you focus your attention on what's left. And you ask yourself, what's the greatest common divisor of these guys? And I think, again, the answer is 1. All right? So since the greatest common divisor is 1, I work towards making that into a 1. And this takes a certain amount of conniving, but you can do it. So I create a 9 here by subtracting twice. And then I flippity-floppity, columns 2 and 3, get this. And then I rescale row 2 by 9. That gets me that. At which point, I can clear this out. Easy peasy, right? But in so doing, I end up putting a cubic down in the 3, 3 spot. right? So row 3 minus x squared minus 9x plus 18, row 2, that puts this down here, right? Then I can use column operations to take this 1 and clear out that x minus 9. It leaves me to this. And there is the Smith normal form for this matrix. This reveals that the minimal polynomial is x times x minus 3 times x minus 6. All right? And that's it. I mean, there's one invariant factor here. It's a 3 by 3 matrix. So one cubic factor is all you get. All right? Now, from a matrix theoretic perspective, there's an easier way to do this. You just calculate the determinant of the matrix, or you calculate the characteristic polynomial of the matrix and factor it. You'd see that it's split linear. I mean, it's got distinct linear factors, which would say it's diagonalizable. And also, since every factor in the characteristic polynomial has to also be in the minimal polynomial, it immediately follows that this must also be equal to the minimal polynomial. Right? If you've only got if you got 3 factors to go with, and they're all, and you have 3 distinct factors in the characteristic polynomial, and you're working with a 3 by 3 matrix, it must also be the minimal polynomial. It's unavoidable, because they have to share the same zeros. That's an example. Here's a kind of simpler one. This is a diagonal matrix. And, this one, I do column 2, 1 minus column 2, add the rows, do that, sweep that out. There you go. So again, sorry, my examples were kind of boring at the start. But thumb and foot doesn't have anything quite this boring, right? This one, a little bit more exciting. Let's see here. Again, x minus 3 and 1, GCD of a constant and a linear polynomial is 1. So I still expect to put a 1 in the upper left. And when I do that, I end up with this. Again, that's the minimal polynomial. Yeah.
And you said that you can get the same answer by taking the determinant of xi minus i?
Well, I think for these, I could just straight calculate the characteristic polynomial as we learned in Math 3 in linear algebra. And we have the Cayley-Hamilton theorem, right? So we know that if we plug in the matrix or the transformation we're talking about into the characteristic polynomial, it works out to 0. So that means it's a contender for being the minimal polynomial. But it may be that there's extra factors that are like repeated in the characteristic that we could strip away and still have it work out to 0. But I think, again, this is one of those examples where the minimal and the characteristic polynomial are equal.
Yeah, it's been the last.
Yeah. But this one is not diagonalizable. Diagonalizable means that, among other things, the minimal polynomial will not have a repeated factor if it's diagonalizable. That's a theorem. Yeah.
So I'm just making sure these equivalent statements are still like in a way row operations. You multiply the top row by -1, and then doing a column operation where you just multiply. You subtract x minus 3 of column 1 from column 2. Like for that very last equivalence there.
Right.
Sure
Yes. The last step would be column 2 is replaced by x minus 3. We're adding x minus 3 times column 1 to column 2.
Okay.
Right.
And then just multiply it by -1.
Yeah, to change that. After that, to change that to a 1. Here's one. If we're working over the real field, we're stuck with, stuck with that. So it's not diagonalizable over the reals. But of course, over the complexes, we could factor that, so it would be diagonalizable, right? Here's a slightly greedier example, 2, 2, 3, 3. And so you go through all these steps, blah, 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 blah. Eventually, I got to this. So in this case, the minimal polynomial is x minus 2 times x minus 3. But the characteristic polynomial is x minus 2 squared times x minus 3 squared. The rational canonical form for this would look like, it would look like the following. So we'd have c of, what's that, x squared minus 5x plus 6, yeah? Which specifically looks like 0, 1, 0. Oh, I can't do math. 0, 1, minus 6, 5. Do I got that right, Liam?
Yes.
Okay. This is the same. This would be the rational canonical form for that example. The larger point is, you can write down rational canonical forms for a given matrix without actually knowing specifically the mechanics of how we similarity transform from the given matrix to that. Describing the precise similarity transformation, which gets you from A to that, is a more difficult calculation, which is far less appropriate for an in-class test. I'm just saying. Your question? Yeah? Oh, zeros. Yes, these are zeros. It's block diagonal. It does matter. Yes, they're zero. This one here, you might recognize as the real Jordan form with a complex eigenvalue of 2 plus or minus 3i. Yeah.
Those, the top left and the bottom right matrices are equal, right?
Yeah, these are equal.
They're the same
Yes.
matrix.
Right.
Okay.
Yeah.
So that is rational canonical form.
In this case, yes. For this one, yep.
So they're equal because you ended up with the same thing in the bottom right and the one right above it?
Right. So the A1 of x was actually equal to A2 of x. The first invariant factor is the minimal polynomial. The second invariant factor was the minimal polynomial in this rather peculiar example. This one here, kind of the same thing, but with, is that right? That's garbage. Nonsense. This is not right. Why is this not right? Junk. This dot, dot, dot is dot, dot wrong. This is a quartic. Game over. End of story. This is a 4 by 4 matrix. So the characteristic polynomial is fourth order. We only get a total of 4 degrees worth of invariant factors. I can't have this and that. If I multiply those together, I've got an 8th order polynomial, which cannot possibly be the characteristic polynomial here. So I think what would happen if I did the calculation correctly, I'd have a 1 here, and I'd just have that. All right? Yeah. And so the rational canonical form here would just look like a 4 by 4 matrix with 1s down the subdiagonal, and whatever this multiplies out to, if you multiply it out, and you can take the minus, like it starts with a minus 169 and so forth. Yeah. All right. This one is a 3 by 3 Jordan block. It works out like that. We'll talk about the Jordan form next class, okay, guys? But so this is what the Jordan block Smith normal form 2. The rational canonical form for this matrix would be like 0, 1, 0, 0, 0, 1. And then what does this multiply out to? Like, it's got a minus 64 for the constant term, right? So the companion matrix would have a 64 like 64, and then whatever the coefficient of the linear term is, and then whatever the coefficient of the quadratic term is. And then, okay, now, so just a bunch of examples in here. While I've got this out, oh my goodness, that's quite the example. This notation is from Rotman. This Langle, Langle, Wrangle, Wrangle, Langle, Langle, V, Wrangle, Wrangle, is the span of these guys. It's what T generates under the fx module action of T. Excuse me, it's what V generates under the fx module action. But anyway, that was not what I wanted to look at. At the very end of this, I think. Oh, nope, wrong one, wrong one. Was it, what was, oh man. Oh, it's this one. Here we go. This I also have posted in Blackboard. And so we talked about this more the other day. I just wanted to mention, you don't need to read the first however many pages of this. It's like most of this PDF is devoted to understanding Rotman's view of modules and comparing and contrasting that to another linear algebra book called Curtis, where he does this kind of halfway thing in between between Jordan form and rational canonical form. That does not matter to you guys. You didn't study Curtis, so you can ignore that. And my point is, the thing that's useful in this PDF is just this last page, because it collects things together from Dummett and Foote that in a way that might be useful to you. So these are the different finite abelian groups of order 1800 up to isomorphism, written either in their elementary divisor form or in their invariant factor form. So there's a whole host of examples here, yeah. So, yeah.
So there's a homework problem that has 5 parts, and each part has a really big number like that. Do we have to make a list like that for each of the 5 parts? Like, do we have to make every list possible for each?
I hear what you're saying, and so I would be happy if you feel like you're bored after you do part A, or maybe after you do part B and you want to stop. I would be fine with that.
Great.
Yeah, I mean, do it as long as you're learning things. Do it. Once you stop learning things, stop.
Okay.
Yeah. Generally true of homework, right? In principle. Now, in practice, this is the abelian group side of things, right? I've been focusing mostly on the fx module induced by the linear transformation today, but I would say that this is sort of connected in some sense to the, this is like the rational canonical form side of thinking, whereas this actually is more like the Jordan form kind of thinking. So that's why we have to have 2 different discussions, one for Jordan form, one for rational canonical form. They're different in kind of the same way these are different, just to make a rough analogy. Okay, now, so I want to show you something, which is, let me put this away. Well, here, yeah, let's see. Ah, check it out. So as promised, I will show you how to calculate the Alexander group of the knot, the quasi-pretzel knot. So here's the way it works. So we'll be back to talking about the linear transformation and all that stuff next time. But Alexander group of knot, or we could say A of K. Let's say K is the knot. All right? So I'll show you a picture. All right, I'm going to try. Here goes. All right, does that make sense, what I've written? I mean, if you can visualize a knot where you've got the string going around here, and then under another loop, over that one, under that one, back around, over that one, under that one, over, back, and under, over, under, over, under, over, under, over, under, over, under, over, under. This is fun. All right, I'll stop. Anyway, do you understand what I mean by the picture? I think. All right. So something really neat is there is a group, an abelian group that is connected to a knot. And it turns out, you can talk about knots being equivalent. All right. So if you have two different knots, they're said to be equivalent if you can change one into the other without untying it. So this is the equivalence of knots. If you can manipulate one into the other without untying, they're said to be equivalent. If the Alexander group of a given pair of knots is not isomorphic, so the Alexander group for one is not isomorphic to the Alexander group of another, that implies, in fact, that means that the knots are inequivalent, that you can't morph one into the other. Now, it's not a one-to-one thing. If the Alexander groups of two knots are equal or isomorphic, it doesn't prove that they're equivalent. It's sort of just a no-go kind of thing. There's not one-to-one correspondence between the isomorphism of Alexander groups and equivalence of knots. But anyway, so the reason I'm bringing this up is it gives you a really neat example of finite abelian groups. All right. And so here it is. The way it works is very simple. We label each region, so like A, B, C, D, and E. And then there's outside, there's F. F is also here. F is also here. Okay, F is outside. All right? And the rule for writing down the equations, I'm going to draw up here how it goes. So I've got this one, got this one, this one, this one, and so I have F, C, A, B. So do you guys see where that's coming from? Let me put a dot where that's from. That's from right here, right? And then I've got BCAD. All right. And then I've got AFDE. And finally, I've got DCEF. Let's see here. The third one? All right, let's see here. A, AF, and AF, that right here. AF. This is over. AF, DE. This is the solid one. Oh, I mean, if you'd rather, I could write FADEED, sure. Yeah, sure. Now, some topological arguments that I don't understand quite in the book, which I found this in. But it has something to do with the Euler's topological theorem, counting edges and faces and such, and envisioning these knots on top of a sphere. Something like that justifies this. But in short, there are topological reasons to write down the following equations. So we have A plus B equal to F plus C from the first one. The second one gives me that B plus C is equal to A plus D. The third one gives me that F plus A is equal to E plus D. And the fourth one gives me that D plus C is equal to E plus F. These are equations. So what you're looking at, you can write down the following relations matrix. 1, 1, minus 1, 0, 0, minus 1, 1, minus 1, minus 1, 1, 0, 0, 1, 0, 0, minus 1, minus 1, 1, 0, 0, 1, 1, minus 1, minus 1. And then you can find the Smith normal form of this over a Z module, though. There's no X involved here. We just do row and column operations, but you have to keep in mind that the only units you have to work with here are plus or minus 1. You can't divide by 2. You can't multiply by 2. All you can do is stuff like, you can clear these out, right? So, what would be the next matrix you'd get? So we get zeros here, right? And what happens? I get what? You guys have to help me out. Minus 2. Oh, minus 2, 0, 1, 0, I think 1. Minus 1, 1, minus 1, minus 1, 2, yeah? And the last row, 0. Oh, nothing to do there, right? The last row just stays unaltered. Then you can do column operations. Clear that out, right? And then you look at then what's left below the first row and the first column. You look at this stuff. You look for what's the GCD of all that. What's the GCD of all that? It's 1, right? You add a 2 and you add a 1. The GCD is 1. Okay? And you just keep doing this, all right? And I have explicit calculations here that I will post. They're wrong though. So I work it out, or either it's wrong, either my calculations are wrong or the book I found this in is wrong. But anyway, it keeps going. And allegedly, eventually, you get to 1, 1, 1, 5. And then zeros in the last column. All right, so the point of this is we start with the equations that are given, right? Start with the equation star. And then by doing row and column operations, we get to this system of equations. And what this means is with respect to some different choice of basis for the space, we have that A prime is equal to 0, B prime is equal to 0, C prime is equal to 0, 5D prime is equal to 0, and then E prime and F prime are free. In other words, if you don't make the mistake I made, because I got a minus 1 in the last thing, which... So allegedly, the Alexander group for the quasi-pretzel here is up to isomorphism Z cross Z cross Z mod 5Z. where the two copies of the integers are from the columns of zeros. The significance of the ones is you're looking at like z mod 1, the principal ideal generated by 1, which is all of z. So like z mod z is 0. So this gives you 0, this gives you 0, this gives you 0, this gives you z mod 5z, which is z5. And then these last two give you the two z's like that. It's not at all obvious what on earth this is as an abelian group. If I said, what is this? No one here is going to say, oh, that describes z cross z5 as a solution set to, 4 integer equations and 6 integer unknowns. Obviously, right? No, not obvious. But this makes it obvious, which is the other principal use of the Smith normal form. It allows us to simplify abelian groups presented by generators and relations. And those are interesting because they come from things like, group knots. So I thought the group knot would be fun because it's, you see how to do it anyway. Oh man, I'm sorry. I'll shut up. I will not be in office hours early Monday because